Hi, welcome back to section, what is this, 3.2? This is our second video in there. We had just taken a look up here about how to calculate the standard deviation. And now we're going to talk about why it's important, why it is such a big thing that we use in statistics. All right, so let's take a look at the rule of thumb for understanding standard deviations. So the range rule of thumb, I don't love that name, but that's what this textbook uses for it, so we'll go with it. But it's a crude but a simple tool for understanding and interpreting standard deviations. And basically the argument is that about 95%, the vast majority, about 95% of sample values lie within two standard deviations of the mean. Okay. Now that 95% there, that is close to an approximation, right? And so we use that then to talk about whether values are significant or not. Okay. Now significant values are values that are either significantly low or significantly high. Values that are significantly low are any values that are more than two standard deviations below the mean, and high is two standard deviations above the mean. Anything in the middle is we just consider it not significant. So what does that mean? Well, let me give you an example, and I'm going to go back to my favorite example. I'm going to go back to my cans of Coke that are supposed to have 12 ounces in them. So let's say that I do some data mining and I gather some information and I find out that the mean value for the amount of soda that is put into a can is 12.01 ounces, okay, with a population standard deviation of 0.02 ounces. Okay. So what that tells me is that if I go down to the production floor and grab a can of Coke, that the predicted mean should be about 12.01 ounces, and that any value between here and here, that is any value between two standard deviations above the mean and two standard deviations below the mean, I would look at that can of soda and go, yeah, that's acceptable. That's where it should be. Nothing's perfect, and 95% of the time I'm going to get values in there, and I'd be okay with that. Now, what is that lower number? What is that lower limit over here that separates the significantly low from not significantly low? Well, it's going to be the mean minus 2 times the standard deviation. So I'm going to grab my calculator, and I'm going to say, well, the mean is 12.01, and I'm going to subtract off 2 times 0.02. So that gives me 11.96. So down here, anything below 11.96, and I would say that is a significantly low value, or in terms of what I'm actually talking about here, I would say, wow, that is a significantly low amount of soda to be in that can. That probably shouldn't be happening. Something's probably wrong. The machine is probably underfilling these cans. The same way I would check for a significantly high value. I would say 12.01 plus 2 times our standard deviation of 0.02. Again, I'm going to grab my calculator. So 12.01 plus 2 times 0.02. And I get 12.05. And I just realized there's a mistake up there in the 12.01 for the lower limit. Minus 2 times 0.02. Do you see the mistake? I didn't put the 0.01 in. It's actually 11.97. So let me fix that. So this one down here is 11.97, not 96. Sorry about that. And this is 12.05. So what does that tell me? Well, it tells me that anything below 11.97 ounces, and we've got a problem. Anything above 12.05 ounces, we also have a problem. Anything below 11.97 ounces and my machine's probably underfilling. Because you think about the numbers now. So I'm going to erase some of this so I can have some space up here. But if we're going with the percentages, there's a 95% chance that if I grab a can, it should fall into that range right there. Which means there's only a 2.5% chance and a 2.5% chance of getting a can that is significantly low or a can that is significantly high. And so in statistics, we tend to use that 95% as our benchmark to say that anything that has a 5% or less chance of occurring, we should question, we should look at. That isn't usual, that is unusual to happen. So these two tails, if you will, the significantly low values and the significantly high values represent that 5%. Whereas the 95% in the middle is the, yeah, we would expect to see that. And that's going to keep coming back again and again and again and again, where we're going to have these scenarios where we're going to say, hey, go measure that. What do you think about your measurement? Is your measurement not significant, or is it significant? And in general, 95% of the time, your value should not be significant, and only about 5% of the time should it be significant, with about 2.5% of the time it being significantly low, and 2.5% of the time being significantly high. So when we're looking at what's going on here, it's oh, what does that tell me? What does it tell me if I go down to the production floor and I grab a can of soda and it comes back and I measure it in my lab and I measure it at 12.04 ounces? Well, 12.04 ounces is about there. So not significant. I would just say, yeah, machine's probably working fine. And I would have to get something that fell outside of those values to make me question whether the machine was working okay or not. Right? There's also another way to estimate your standard deviation. It is a rough estimate, but if you needed a quick estimation for a standard deviation, you could take the range of your data set and divide it by 4. We don't use this very often, especially now because we have tech. Remember when we did this in the calculator, how fast it was? Why approximate it if I can find it quickly? Right? All right, let's move on. The standard deviation of a population. Okay, so let's say that you have data and your data is the entire population. Well, you might need to find the standard deviation of that data. And so how would you do it? You would use this formula right here. Now you'll notice that this formula looks a lot like the standard deviation formula. The standard deviation formula had that summation in the numerator, and it had n-1 in the denominator. So there are two things that are different here. One, we're swapping out our sample size, and two, we're swapping out what we're using for the mean. Right? If you have population data, then you would know the population mean, and that's why you're using the population mean right there. If you have sample data, you would have the sample mean, and that's why we've got the sample mean there. If you have population data, you would know the actual size of the population there. If you have sample data, you always use n-1 because it helps adjust for it being a bias estimator, so that is a bias adjustment. Right? And if you really want to know why n-1 is a bias adjustment, we can meet up for office hours and I can have a conversation with you about it. Right? It's a long conversation. Just accept that by subtracting 1 from the sample size, it makes the standard deviation a better estimator for the population standard deviation. We don't do this very often. And the reason we don't do it very often is we don't know population population data very often, right? When we did the calculation on the calculator, remember when we went to the one variable stats and we ran that calculation, the calculator finds the population mean and the sample mean for you. And the reason it does that is it doesn't know the difference between your data sets. When you type in a data set to the calculator, there was no little toggle to say, oh, and by the way, this is a sample, or oh, and by the way, this is a population. So it calculates them both. If your data happened to be a population, you would use the 14.7. If your data was the sample, you'd use the 16.5 there. Okay? Now, someone might be thinking, well, why isn't there a mu on the calculator? Well, the reason is that the formula for the mean is the same whether your data is a population or whether your data is a sample. So that X bar that's at the top, that's 30.74 up there, if your data was a population data set, you would just report that as mu equals 30.74. And if your data was a sample data set, you would report that as X bar equals 30.74. If your data was population data, then you would just say that the population standard deviation is 14.72. If it was sample data, you would say it's 16.45. And we just have to interpret it. The calculator is a dumb tool. It does things that it can do really, really well, but we still need someone with brains on this side of it to interpret what it's telling us. Okay? All right, the variance. Okay. The population variance and the sample variance are two calculations that you can find by taking the square of the standard deviation. Right? So if S is the standard deviation, when you square it, you get the variance. Right? If sigma is the population standard deviation, when you square it, you get the population variance. Right? Why do we do this? Why do we care about variances? Well, it's this one right here. When we square our sample standard deviation, it becomes an unbiased estimator. And because it is an unbiased estimator, we can use S squared, the sample variance, to estimate the population variance. Or we can also use it to predict. Now, when we get to the hypothesis testing section of this later, we'll actually be doing that. What does it mean for us? Well, sometimes we need to know this. And if we were calculating things by hand, it would just be a step in the process. I'm going to go back up here to when we actually calculated that standard deviation by hand. Right here, this number, I'm going to highlight it in pink. The 270.763, before we took the square root, that was the variance. And we had to take the square root to get the standard deviation. So if you're calculating things by hand, the variance just naturally shows up because it's part of the process. It's the last step before you take the square root. Right? Now, if you're using the calculator, unfortunately, when you use the calculator, there is no variance. So what one has to do, what you will have to do, or what I would have to do, is if I wanted the variance, I'd have to take the standard deviation from the calculator, that's 16.45 or that 14.71, and then I'd have to square it. Now, one thing I want to point out, okay, and I'm just going to copy a number down here real quick so we can talk about this. On the calculator, the standard deviation is 16.45487777. Now, I know that the rule for standard deviation says to round to 2 decimal places for this data set because that will be one more than the accuracy of the original data. But I want to show you something. Right? if I just take 16.45 and I square it, here's what I'm going to get. But if I take 16.455, which would be that number rounded to 3 decimal places and square it, here's what I get. And if I were to take 16.4549, 4 decimal places, and square it, here's what I get. Do you notice how using more gives me a more accurate answer? Well, I shouldn't say more accurate answer, but I would have more accuracy in my final answer by using more accuracy in my number that I use for my calculation. So while reporting the standard deviation would only require those two, if I want to turn it into the variance, I wouldn't round it until I turned it into the variance. So I would take that 16.4548777, square that, and then I would round that answer and see that I'm looking at 270.76, which is very different than what I would have gotten up here. I would have got 270.65 if I only used 2 decimal places before I rounded, or before I squared, sorry. That's enough for an answer to be wrong. And it's definitely enough to cause problems with the calculations. So anytime you're turning either a sample standard deviation or a population standard deviation into a variance, take a whole bunch of decimal places, square it, then round. If you round first, you're really going to get wrong answers. And that's the best way I can say it. Okay? All right. Where this is all heading and where we're going with this is something called the empirical rule, which is going to become very important later in this course. We're going to be doing a whole bunch of this. And the empirical rule allows us to use means and standard deviations to talk about data sets. But specifically, it's talking about data sets that have a distribution that is approximately bell-shaped or approximately normal or approximately normally distributed. Those are 3 different phrases or words that you'll hear that describe this. And the empirical rule tells us that if you have data that is normal or approximately normal or normally distributed or bell-shaped, that this math representation down here will be true for your data set. That is, that if you have a known mean and a known standard deviation, that if you go 1 standard deviation above or below the mean, that middle chunk right there of your distribution is going to represent about 68% of the data. If you go 2 standard deviations, you'll be looking at 95. So that's 2 standard deviations below to 2 standard deviations above. If you go 3 out, now you're looking at 99.7% of the data. So you're going 3 standard deviations below and 3 standard deviations above. Okay? If 99.7% of the data is within 3 standard deviations, basically what we're saying is there's nothing out there beyond that. I know it's not technically nothing. Down here on the low end, there's technically about 0.13% below that 3rd standard deviation. And similarly, there's also about 0.13% on the high end. It's closer to 1.5 if we use the numbers, right? All of these numbers that are here are approximations. If you added all these numbers across here up, you would get something really, really close to 100%, if not exactly. But the math doesn't math with these numbers. Because if I do 100 minus 99.7, I get 0.3%. And if I take that 0.3% and I divide that by 2, I get 0.15%. So this out here really should be 0.15% if I trust that 99.7, right? So when you're looking at these, know that these numbers are, they're accurate, right? But they're approximations as well. They've been rounded to work. On this image right here, these numbers down here are the most accurate. And you can definitely see it right here in the middle. If I take those two and I add them together, 34 and 34 is 68. So I'm going to get 68. 0.13 and 13 is 26.26%. Whereas this says it's only 68%. It's actually closer to 68.26%. Why do we call it 68 if it's 68.26? Because 68 is a nice number and 68.26 isn't as nice. So we round it and say about 68%. Right? And if we go 2 more standard deviations out, it says 95%. If you add all those up, so if we add up the 13, well, let me clear this so it's not as ugly. That 13.59 plus that 34.13 plus another 34.13 plus another 13.59, I get 95.44 instead of 95. And if I add in the 2.14 from the left over here, this guy, and the corresponding 2.14 from the right, I get 99.72 instead of 99.7. So do you see how it's a little bit off? Okay. So the numbers across the bottom here, like I said, are more accurate than the 68, 95, 99, 7. But almost every textbook and almost every stats class you'll ever be exposed to will tell you 68, 95, 99, 7 because those numbers are nice and easy. Okay? A little bit later in the semester, we'll do the actual calculations to find all these values, and you'll see how, if you actually cared about high degrees of accuracy, you could find those values that are much more accurate. You should think of these numbers here as approximations, but good approximations. Okay? All right, let's put this into an example and come up with our use our empirical rule to answer a question. Okay. All right, this problem reads that IQ scores have a bell-shaped distribution and a mean of 100 with a standard deviation of 15. All right, so first off, I want to point out something. Okay. Right here, it defines a mean. Does it tell us whether that's a population mean or a sample mean? And I can't see in here where it says. So I am going to assume that it means the sample mean since I don't know for certain it's a population mean. It also mentions the standard deviation here. Again, since I don't know it's a population standard deviation, I'll assume it's a sample standard deviation. Not because of anything other than it's safer to assume that it's sample stuff than it is to assume that it's population stuff. Okay? All right. It's asking us what percentage of IQ scores are between 70 and 130. Now, there's a clue right there. So since it tells us we're using the empirical rule, we're going to use this thing up here. And I'm going to start filling in some numbers. So I was told that this middle is 100. And since the standard deviation is 15, this would be 115. And this would be 130. And this would be 145. And so again, similarly, since the standard deviation is 15, this would be 85. And this would be 70. And this would be 55. I'm just adding or subtracting standard deviations based on what it tells me to do. So what does this layout up here on this graph tell me? Well, It tells me that about 68% of the people have an IQ between 85 and 115. Or if I go 2 standard deviations out, 70 to 130 is about 95% of the people. So the statements that I could make would be about 68% of, what are we looking at, people have an IQ between, what is that, 85 and 115. I could go 2 standard deviations out and say about 95% of people have an IQ between 70 and 130. Okay. Could I go 3 standard deviations out and say about, whoops, I want to change colors. 99.7% of people have an IQ between 55 and 145. Okay. So what does this mean? Why would I care about this? Well, this is a pretty quick and dirty, crude way to approximate things. I could then say, hey, if I go out on the street and grab a random individual, I've got about a 68% chance of grabbing someone who has an IQ between 85 and 115. Or a 95% chance of grabbing someone between 70 and 130. Or a 99.7% chance of grabbing someone between 55 and 145. And because of the nature of the symmetry of this graph, if I wanted to, I could find the probability for this range right here. I could say, what's 100 to 130? And you would look at me and say, well, that's just the 34 plus the 13. So you're looking at what, 47.7% or so? Or I could say, what's the chance that I'll grab someone who has an IQ between 55 and 100? And you would say, okay, well, just add up those 3 numbers right there, and you'd be looking at that probability. Or if I randomly grab someone, what's the chance their IQ is above 145? Well, that's that 0.13. So I could rip this thing apart into whatever pieces I want. So while the rule is written to talk about symmetry, 2 below, 1 below, 3 below, that kind of thing, to 3 above, 2 above, 3 above, that kind of business. Okay, this symmetry, we can also use it for non-symmetric representations as well. All right, this brings us to the end of section 3.2. I'll see you back here for section 3.3. Have a good day.